In solid mechanics, pushing a ductile metal past its yield stress causes permanent deformation. Structurally, the component has failed. Yet inside industrial facilities, dealing with high pressures and extreme temperatures, this standard logic collapses. Designing a high-temperature steam line to remain strictly below its yield point during thermal expansion would require massive routing loops. The sheer volume of material and space required to accommodate that flexibility would render most plants economically unviable. To solve this, ASME B31.3 introduces a calculated exception. It expands the allowable limit for thermal stresses to twice the material's yield strength. This requires engineers to discard the idea that all stress behaves identically, separating forces demanding equilibrium from strains dictated by physical displacement. Industrial pipe design sidesteps traditional failure by mathematically categorizing stress and engineering exactly where and how local yielding occurs. To make that localized yielding safe, ASME codes separate all imposed loads into three exact categories: primary, secondary, and peak. Primary stresses are force-driven. They're the direct result of internal pressure and the pipe's dead weight, demanding basic mechanical equilibrium. Because these loads are constant, primary stresses are not self-limiting. If the stress exceeds the yield strength across the entire cross-section of the pipe wall, the material will stretch continuously until catastrophic collapse. Secondary stresses are strain-driven. They develop when a structure's physical displacement, almost exclusively due to thermal expansion, is constrained by its supports. Peak stresses are the highest localized points of stress concentration. Found at structural discontinuities or sharp thermal gradients, they do not distort the pipe's gross shape, but they initiate microcracks in the metal. Each mechanism threatens the system's integrity differently, demanding a separate mathematical limit to prevent its specific mode of failure. For primary stress, the ultimate failure mode is plastic instability, the physical bursting or total structural collapse of the system. This chart plots the limit stress for a rectangular section under combined tension and bending. To prevent gross failure, piping codes rely on this limit design theory to handle primary loading. When the average tensile stress is 0, the failure limit under pure bending sits at 1.5 times the yield stress. As the tensile load increases across the section, the threshold for failure bends sharply downward toward a strict yield constraint. By setting strict boundaries, such as capping the general primary membrane stress at 2/3 of the material's yield point, ASME B31 locks in an adequate safety factor against this gross limit load. These primary load limits operate as constraints, ensuring the pipe structure holds its own weight and contains its internal pressure without buckling. Secondary stress ignores those rigid safety factors entirely. Because a secondary load is generated by the pipe fighting its own geometric constraints, rather than an external mass, local plastic yielding actually relieves the stress in the system. This counterintuitive behavior is governed by the elastic shakedown theorem, the exact mechanical justification for allowing thermal stresses to reach twice the yield point. As the plant heats to operating temperature, the constrained pipe is forced to yield slightly in tension. It stretches beyond its physical yield point to a new theoretical strain. If the pipe behaved perfectly elastically, the calculated stress at this exact strain would project far above the material's actual physical yield line. When the plant cools down, the contraction does not retrace the plastic path. The stress-strain curve drops perfectly parallel to the initial elastic line, plunging through 0 and into negative territory. Returning the physical pipe to 0 strain forces the now plastically stretched material into a state of residual compressive stress. On the next thermal cycle, the heating pipe must overcome this residual compression before it can even enter tension. The initial cycle has effectively expanded the pipe's functional elastic range. As long as the calculated pseudo-elastic stress remains under twice the yield point, the system safely shakes down to purely elastic action after a few operational cycles, preventing continuous incremental deformation. In an operating plant, primary and secondary load cases do not exist in isolation. They interact dynamically. Consider a standard piping run resting on multiple single-acting vertical supports, designed to handle the primary dead weight of the steel and fluid. When the system heats up, thermal expansion forces the pipe to bow. The displacement causes the pipe to physically lift off the central vertical support. The dead weight that central support was carrying is instantly transferred to the adjacent nodes, shifting the primary sustained stress profile of the entire span. A secondary thermal displacement has triggered a primary stress spike. If the engineer isolates the load cases and fails to model this dynamic liftoff, the pipe collapses. The final stress category governs long-term degradation. The shakedown theorem halts gross plastic ratcheting, but repeated thermal cycling continuously stresses the local discontinuities in the pipe, slowly initiating microcracks over years of operation. This is a logarithmic SN fatigue curve, showing the typical relationship among stress, strain, and cycles to failure. To calculate the finite lifespan of the pipe, engineers use data derived from strain control testing. This data allows designers to convert calculated physical strains into pseudostress amplitudes. This guarantees the pipe alternating stresses remain low enough to survive a specified number of operational cycles without rupturing. Primary and secondary limits ensure the pipe maintains its physical shape today. Peak stress limits act as a structural countdown clock, defining the absolute operational lifespan of the entire facility. Passing the mathematical stress limits required by the ASME V31.3 code is only a fraction of the pipe stress engineer's mandate. A viable industrial design requires balancing three strict constraints. Code stresses must pass the math, physical displacements must be carefully controlled, and forces exerted on terminal equipment must be restricted. A system can be designed with massive expansion loops that easily pass the secondary stress code. However, that flexibility transfers the thermal load directly into the fragile nozzles of attached components, destroying the equipment it is supposed to service. Piping design is the proactive, mathematical management of where structural energy is stored, yielded, and dissipated safely across an industrial facility.